Hey, welcome back. Let's take a look in this lesson on what we call resonance structures. So, we're in this lesson right now. What we're doing is focusing a little bit more. This is related to our series where we're looking at how different type of molecules have three dimensions. And so, if you haven't watched that lesson yet, if you have, there's actually a few lessons I have. If you haven't gone and looked at the lessons for like Lewis structures, taking a look at Lewis structures that are more complex than just a simple atom, but where molecules form, molecular compounds, things of that nature. You're going to want to take a look at those lessons first, because I'm going to be drawing on those concepts here in this lesson. So the link that you'll see, and it'll also be in the description, go back, take a look at that. It's also in the playlist that deals with molecules and bonding and stuff like that. So let's just go ahead and jump in. So resonance structures, it's important for us to just really break it down and understand what in the world we're talking about when we say a resonance structure. So structures, we just know means it's going to take a certain form. It's going to take a certain shape, right? And then resonance, we really need to understand what that means. Well, let's think about outside of chemistry class, outside of science, when we talk about if we hear a song, we say, it might be said that it resonates with you. There's something about the words, there's something about the sound, it resonates with you. If you see a painting, see some form of art that really sort of moves you inside, you feel a connection to it, you might say something about it that resonates with you. It stays with you. It causes a movement within you. And so we loosely interpret it that way in the sense of what resonate means. Here in chemistry, when we're talking about the physics and chemistry behind what's around us, matter in this case, resonance, it still has that same connotation, but it is much more literal, where something about the structure is resonating, it is vibrating, it is moving. It's not static, and no molecules are static. We know that that all molecules, even this desk, my glasses, this pencil, this delicious cup of coffee, all matter. It doesn't matter if it's in solid form or a gaseous or liquid form. The molecules are vibrating, they're moving, and because you've got all those electrons that are in these various spaces all around the nucleus, right? So with resonance structures, the same thing is happening. Those electrons, they're not stuck. When you draw a Bohr model, right? So you remember, we draw a Bohr model. So, that represents the nucleus, and then you've got, the first orbital, you got the second orbital, and there could be, there's 2 electrons in the first orbital, right? And you can have up to 8 in your other orbitals, as far as counting valence electrons. Those electrons aren't just stuck in that place, in that place, in that place, in that place. They're moving everywhere. They're orbiting everywhere. There's a probability that they're here. Say this, my fist right now represents the nucleus of this atom. Those electrons, they could be here, they could be here, or here, or here, or here, or here. They could be in any region. They're just not in this sort of fixed rotation and statically frozen in the space within that rotation, right? Statically meaning stasis, they're not moving. We know that's not true, right? And so you know the whole electron cloud theory. You're familiar with that, right? So knowing that means that when we look at Lewis structures, if we follow the rules that we've been using, if we follow what we know is true, what we see mimicked in molecules in nature, then we find that there's times where there's multiple forms that might show up. And so when we're looking at a resonance structure, there's going to end up being multiple forms. There's going to be more than one. So that means there's going to be at least two. There's going to be at least two structures. Sometimes you can have three. Sometimes, depending on the complexity of the molecule, you might wind up with four. So in class, we will take a look, and in these lessons, we will take a look at some different types. And then, on assessments, you might get things that have 2, 3, 4, or whatever. But as a rule of thumb, usually 2 or 3. All right. So let's just jump in and do an example. In a previous lesson, we already worked with carbon dioxide. All right. We already worked with carbon dioxide. And so we now know that, with carbon dioxide, we saw that we got a form that looked something like this. Okay? So again, if you hadn't watched those videos, I just gave it away. In the previous lesson, I talked about how we get to that. In class, we talk about this. So you're going to want to go back and take a look at that. So we already know that this is true. We already remember rule 1, right? Remember, rule 1 is sum the valence electrons, right? Sum all the valence electrons. Rule 2, remember we said you just need to bond the atoms, all right? And here when I'm writing, I'm abbreviating. I'm sort of shorthanding what we know is the process, right? And then rule 3 is we have to satisfy the octet. And that means the octet for every atom that is bonded. Hydrogen being the exception, because remember it follows what we call a duet rule, right? So because there's only one orbital, 2 spaces, so there can only be 2 electrons in the first orbital, right? So that's the exception. So understanding that, then let's move this out of the way. Let's go ahead and leave our rules right up there, just so we can refer to those. And I'm going to go in and clean that up. I wrote that kind of quickly. There we go. Now we can see that. So let's revisit this. We have this structure here, right? So remember, taking a look at this, we have 4 bonding pairs. So there's 8 electrons in our bonding pairs. And we have 4 lone pairs. That's 8 electrons in our lone pairs. 8 and 8 is 16. So remember when we did our work, for rule 1, then we had carbon and 2 oxygens, right? So 1 carbon, 2 oxygens, right? So 4 valence electrons, 6 valence electrons. That's 4. 6 times 2 is 12, right? There's our 16 electrons, rule 1. So resonance structures do not break any of these 3 rules. So I'm telling you that there's resonance form for carbon dioxide. That's the reason why I'm using it in this video. All right. So what we have to do now is ask ourselves, if there were a different form, what would happen? Knowing that all of these electrons that are there, whether they're in the bonds or in the lone pairs, that they're vibrating and moving, that means they're shifting from one atom to another. That means at any one time, hang on, I need to get up and go. At any one time, those electrons, they're moving over. There's a constant push and pull. There's a lesson in a future lesson coming up that'll help tie this all in. And I don't talk about it until a later date because we need to understand Lewis structures to really fully understand that concept. But you've heard of polarity, right? So you've heard of polarity. Well, when things are polar, polar means side or end. And so different atoms have a different ability to push and pull on any other atom that they come into contact with. They come near. And that constant push and pull by all the atoms is what causes them, is what attracts them and brings them close enough together to where those atoms, there'll be a space in between those atoms, and that's where the bonds occur. And we call that the bond, where the bonding pairs are. So that's that shared valence space, right? Covalent bonding area. And then if it's not between two atoms, so if you just got this one atom, then all this space around it, wherever electrons sort of are, we think of them the concept of pairing up in a region of space at any one time. They're alone. They're not in between atoms. So we call those the lone pairs, right? So looking at this, we ask ourselves, is there another way to draw this? Obviously there is. That's the purpose of this lesson. So let's go back to rule 2, which is bond everything together. So now we have to ask ourselves, okay, if we take a look at this first one right here, all right, we have a double bond on either side of the carbon. So that means something's going to have to be bonded differently. So that means we can't have two double bonds, otherwise we wouldn't have a different structure. So going back to rule 2, if we put lone pairs everywhere to satisfy the octet, we would get this right here, because we can see that there's 8 around this atom, we can see that there's 8 around this atom, and we can see that there's 8 around this atom. Again, if you haven't watched those other videos, they explain how we count to get those, so you're going to want to go back and watch those. So this doesn't work because we've got, if you count all the lone pairs here, we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2 is 16. Well, that's already that, plus those two bonding pairs. There's another 4. That's 20 electrons. So we know that this is not a resonance form. This isn't even a structure yet because it's not stable. It doesn't have the correct number of electrons. All right, so let's back all this up. So that means that something has to change. And the only thing that can change when you have too many electrons is the number of bonds. So so let's think about this. If we did this right here, and let's satisfy rule 2, bonding everything together. Well, right now around this oxygen right here, there's a total of 4 valence electrons. I'll be right back. 4 valence electrons around that oxygen atom right now, all right? Or, I'm sorry, there's 4 electrons in bonding pairs right there. That light messed me up coming back. I forgot where I was going with my last statement. So, all we would end up doing would be rebonding this one the same way. So let's think about this. What if we did something like this? What if we put 3 in between the carbon and the oxygen? Now we would see a total of 6 valence electrons between the carbon and that oxygen right there. And now if we looked at this carbon atom right here, it has a total of 2, 4, 6, 8 electrons. Its octet is satisfied. It's just satisfied with no lone pairs. So now let's look at the oxygen over there that's triple bonded. We can see 2, 4, 6. Now there's 8. Now that oxygen, it has 8. Let's come back over here to this other oxygen on the left that's single bonded. If it were to remain single bonded, right, then we would have to have 3 lone pairs. That'd be 6 more electrons. Well, let's see how many electrons we have so far. If we look at our bonding pairs, we have a total of, right now we have a total of 2, 4, 6, 8. Then these 2 right here, there's 10. We need 6 more electrons. And we just said that if we added 3 lone pairs to that remaining oxygen, that would be 6 electrons. So it looks like we could come over here and put a lone pair here, a lone pair here, a lone pair here, and we've satisfied the octet rule for that oxygen. We've also not broken rule 1, which is having 16 electrons for this molecule. And so we realize now this is a molecule. This is a form. We would call this a resonance form. This is a resonance structure, all right? So now let's think about this one step further. If we look at that oxygen atom, we realize that there's two oxygen atoms, so that means there's two different oxygens. They're both not the same oxygen. So if we step back from that thinking, we realize that if we go back to where we were with Rule 2, that there's nothing that says that we could not have just put that triple bond on that other oxygen first. So we could hypothetically call this oxygen number 1 and this oxygen number 2, right? So in the first example up here, I had up at the top, right up here, what I had done was put the triple bond on oxygen 2. Right now I've got it on oxygen 1, right? So they're by technically bonding it this way, this is a different form. Now we realize that we need a lone pair here, and then we go back and we put our lone pairs here, and we now have what seems to be 3 resonance forms, 3 resonance structures. Understanding the concept that molecules are vibrating, atoms are vibrating due to the electrons moving and the energy from that, this constant motion, this constant movement, we need to now show that it's moving back and forth between these different molecules. And the way we do that, it's very simple. We literally just show the movement by saying it's moving from here to here, but it's also moving back. And then in the center right here, this is also moving to here, and then it's also moving back. It's constantly shifting back and forth, back and forth, back and forth. It's happening at a very fast rate. It's vibrating back and forth. It's vibrating back and forth, back and forth, back and forth, back and forth, right? And I draw this one in the center because looking at it, it looks the most symmetrical. It looks, and it is, it's the most stable form. And most of the time, the molecule is spent in that structural form. But it does, depending on the circumstances, depending on the amount of energy that's surrounding the molecule, depending on other molecules around it, there are other things that can cause polarities to shift. And that's another lesson. It causes movements of electrons, and sometimes electrons shift back and forth to opposite sides, polar regions, so to speak, of a molecule. And so these arrows represent that movement back and forth, and to show that that's what's happening. So if by chance we had never talked about carbon dioxide and you were on an assessment, or you and I were at a coffee shop just sitting down chatting together, and I was like, hey, draw me out the resonance structure for carbon dioxide, you would sit down, you would follow rules 1, 2, and 3, and then you would end up doing something like this, and you'd be done. And you'd be able to support your claim as to why this shows the resonance structure for carbon dioxide. All right. So let's do another one. Let's do another one. All right. I'm going to go shift that light before I get started on this next thing here. Let's take a look at a nitrite ion. All right. So in previous lessons, we've looked at structures for just Lewis structures for molecules and for polyatomic ions. So it just seemed fitting to do an example of each here, right? So we've got the nitrite ion. Those Apple pencils are slippery. I love this wonderful. So we've got a nitrite ion. So rule 1, we've got our nitrogen, we've got our oxygen, right? And so there's 1 of these and 2 of these. So remember, there's 6 valence electrons for oxygen, and then nitrogen has what? 5, so that's 5, and 6 times 2 is 12, so that's what? 17 electrons. And then remember, it's negative, so that means it must have taken away from somewhere else 1 electron. So that means we have to add in 1 electron. So we'll need a total of 18 electrons for this thing to work. All right. So let's think about this for a second. All right. We've got rule 2. We've got nitrogen, and then we've got the 2 oxygens. So it makes sense that we're going to want to bond the 2 oxygens to that. Now if we follow, so that's 4, right? So minus 4 electrons. So we need 14 more electrons somewhere. Follow rule 2, that means we would bond, we would add lone pairs, we would add lone pairs, following rule 3 now, until we satisfy the octet rule. We can see that the octet rule is satisfied for all 3 atoms. But now let's see what we've got. 1, 2, 3, or that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It's not going to work. So, once again, too many electrons, need more bonds. All right? So, let's think about this for a second. Obviously, we need to double bond. And so if we go back to what we know about, and here's something you can use to help do some pre-planning for your thinking. If you go back to the earliest lesson on Lewis structures for just a single atom, we know that that's the Lewis structure for nitrogen. Nitrogen wants to form up to 3 bonds. So it makes sense that what we've got right here is working out, and it makes sense that there would be a lone pair on that nitrogen still, because there's already a lone pair on the nitrogen, so that lone pair didn't go away. So I'm going to add that one back in. And that one's probably going to stay. I mean, it makes sense considering that the single atom by itself already has a lone pair, right? All right, so now let's see what we can do here to satisfy the octet rule. And if we look at nitrogen right now, right, there's 2, 4, 6, 8. Octet rule is satisfied with that central atom. And the central atom, once you get that set, usually from there, it makes it a lot easier to work out everything else. So let's go to the atom, the oxygen atom that's double bonded, right? All right, it's to my right on, for me, it's to my right. While you're watching this video, it probably is in that direction. Let's go to the double bonded oxygen. It already has 4 valence electrons with the 2 bonding pairs, so it needs 4 more. So that would be, So that would be 6, 8, all right? And then the oxygen on the single bonded one, we'll call that oxygen 1. Then 2, 4, 6. So now what do we have? We have 2, 4, 6, 8, 10, 12, 14, 16, 18, which is how many we need to start with. We're good to go, all right? So let's get rid of all of this. Now, this is an ion, right? So what do we do with ions? We put them in brackets. You should already kind of be able to see here that, wait a minute, that double bond, just like on the carbon dioxide, when those bonds shifted back and forth, this double bond here probably can shift to that other oxygen. Well, so let's go ahead and do that. So on this oxygen here, and this one, well, it's shifted. So we realize that that'll work. Once again, bracket, because it's an ion, and it's resonating back and forth this way to this way. We are done. We are good to go. All right. So now let's take a look at one more thing. I have asked you in the lessons, and if you have physically have me in class as well, we talk about this extensively. These molecules have 3 dimensions. I'll be back. These molecules are 3-dimensional. So nitrogen, it's blue. So let's go ahead and build this and see what happens. So nitrogen is blue. So we can see that there's a double bond, all right, going to an oxygen atom. And so I'm going to now double bond this nitrogen to an oxygen atom, all right. This is a new kit. So there's there is the nitrogen double bonded, right, to the oxygen atom. So now we also see that it's single bonded, right, to another oxygen atom, all right? And I need this oxygen atom. One moment, this oxygen atom is not the right type. There's multiple types. We'll talk about that later. So now we're bonding here to this other oxygen atom. And if you look at the top, I'm on the top structure right now. This is sort of looking like the top structure. I've got the nitrogen double bonded to an oxygen, single bonded to another oxygen. And then this one over here, we can see has two lone pairs. And these little paddles that are shaped this way, we've talked about why it has that shape, right? Because the electrons spread out. So we can represent those other lone pairs by adding in these paddles. So it's because it's taking up some space, right? And then if we come over here, we go to this single bonded oxygen, right? Then we see that there's 3 lone pairs on this one. And now we have our nitrite ion. Here's the centralized nitrogen. Oops, almost forgot. Lone pair up top, so now I can use that to hold it. So remember, these lone pairs are shaped this way, where the lone pairs are, because when you get closer to a nucleus, here's the 2 electrons, and so they're, let's just say right here, this area here, this is the nucleus. 2 electrons are here, but as electrons get further away, since they're negative, they want to repel each other. So as they get further away from the nucleus, they repel each other. So you can kind of see that there's that pattern that kind of looks like that paddle look, right? And that's why they're drawn this way. And so that's why the standard, you'll see it that way everywhere you go. So there's the nitrogen with its lone pair. Here's that oxygen that has the 3 lone pairs, and then double bonded oxygen that has the 2 lone pairs. Well, this shape looks a lot different than what we have here on paper. So let's make this shape look like this, right? So we've got the nitrogen, right? And then it's angled on this way. And remember, single bonds are longer than double bonds, so I'm actually going to draw those double bonds shorter. And we can see here that is the shape that it takes. I'm going to come back and I'm going to put my bracket. Now, I could, if I just did this, I end up having the other molecule. But I do realize that for some of you, just doing that, you're going to say, wait a minute, then that's not a different structure because you still have the same oxygen atoms bonded the same way, okay? So let's prove our point. What I'm going to do is break the bond, double bond on one of those oxygens there. If I remove this, then I see that now going to this other oxygen atom, it double bonds. And so that means the other electrons shifted over here to this side. And now you can see that here on screen, double bonded the opposite oxygen atom. So that means I'm going to come down here and I'm going to do the same here. I'm going to show that can be the case, right? I'm going to show that. So we're going to put our nitrogen back in the center. Oh, and on the top, I forgot to add those lone pairs there. Sorry about that. Come over here, put our double bond, which is shorter. Put the single bond. We're going to accentuate it, make it longer. And I'll expect that on assessments you do that. All right? And any chemistry instructor is going to insist that you do that, right? Because that's what happens. So there's the resonance structure for our nitrite ion. There's those 2 forms, and it's resonating back and forth between those 2 forms because the electrons are not static. All right? So I hope this helped. If you haven't already bought yourself a molecule kit, you should do so. If you're in my class, all you have to do is go to the planning guide, and the planning guide up at the top on the first page, I have a link to the same kits that I use here in class. They're really good and they're very affordable. There's some really expensive ones out there that are very nice. These are sort of moderately, they're very, very affordable. You can usually sometimes get them on sale. But for the kit that I have listed for you, it's somewhere in like the mid $20s, and that'll be some of the best $20 you've ever spent as far as it's helping you think. It's basically Legos. And I know Legos are, they're a copyrighted thing. So, but Legos, these are chemical Legos. If you buy yourself one of these, you're just playing with chemical Legos. You're just building stuff. And we do that when we're kids. We tend to just get in there and grab things and move things around, and we just sort of learn by doing. We go, oh, that doesn't fit there. Oh, that fits there. Hey, wait, that looks different than the other one. Oh, I see why that happened. And if you do more and more of that, eventually, in your mind's eye, you can see all these molecules. You can just sort of, you don't have to close your eyes to do it, but you can see the structure here, and you can shift atoms and electrons and bonds and stuff like that back and forth and be able to see these structures and be able to put them on paper. So I hope this helped. It's always good learning with you. Thank you for stopping by. I'll see you in another lesson really, really soon. Stay curious and take care. Later.